Oxidation-reduction reactions. We're in a series of talking about different kinds of reactions. So oxidation reduction, that's a long description, a lot of syllables, and so we often call these redox. That always reminds me of Redbox and makes me want to eat popcorn. But they're redox reaction, that stands for reduction and oxidation. In an oxidation-reduction reaction, we get electrons being transferred from one of the reactants to another of the reactants. And that's what defines it as an oxidation-reduction reaction. Many of these reactions involve something reacting with oxygen. But you can have redox reactions that do not involve oxygen. Here we have iron reacting with oxygen to form iron oxide. This is rusting, and that's a redox reaction. Octane burning, any combustion reaction is going to be a redox reaction. Here we have hydrogen and oxygen reacting to form water. Those are redox reactions. Here's an illustration of what happens when you mix hydrogen and oxygen. So here we have a balloon full of hydrogen gas and oxygen gas. And if we give that a little spark with a flame, it will react spontaneously and explosively and rather loudly. And you'll get this very briefly, and then it goes away. It makes water. That's a redox reaction. An example of a combustion one involving oxygen. Redox can also happen without oxygen. So here we have sodium, metal, and chlorine gas. These are a metal and a nonmetal, two elements, and they will react and form sodium chloride. This is a redox reaction also. Electrons have been transferred. We started with sodium atoms, chlorine molecules. We end up with sodium ions and chloride ions. The sodium ion lost an electron. It was transferred to one of the chlorine atoms. That makes it a redox reaction. When we have a metal reacting with a nonmetal, it's going to be a redox reaction. We just saw an illustration of sodium with chlorine. That would be this one right here. Sodium will also react with oxygen. Oxygen is a nonmetal. What's happening here is we have these free elements, atoms of sodium, molecules of oxygen or chlorine, and they're forming ions. Now, this compound, Na2O, that's the correct formula for it. This looks kind of messy and confusing, doesn't it? Because now we've got the charges in there. I included the charges just to illustrate we've got sodium ions and we've got oxide ions. How did the oxygen become an ion? It gained an electron. It actually gained 2 electrons. How did sodium become an ion? It lost an electron. There was a transfer of electrons. That's always going to happen when you have a metal and a nonmetal reacting, because what kind of compounds are formed between metals and nonmetals? Ionic compounds. And the way you get ions is by transferring electrons. So you have to have atoms gaining or losing electrons in order to make the ions. Electrons are not something that can just be hanging out. You can't just lose them, or there's no electron bank where you can go and make a withdrawal and get some electrons. There's no electron homeless shelter for pets that nobody wants anymore where you can go and dump your electrons. Electrons have to be between, they're on an atom or an ion. So if one atom loses an electron, there must be another one to accept it. Otherwise, the first one can't lose it. So this oxidation and reduction is always paired together, a loss and a gain of electrons. We say that atoms that lose electrons are oxidized. Atoms that gain electrons are reduced. So when we look here and we see that the sodium, by becoming a sodium ion, it has lost an electron. That's oxidation. The chlorine has gained electrons. That's reduction. So that can be tricky to remember. So we have a mnemonic, oil rig, OILRIG. Oxidation is loss of electrons. Reduction is gain of electrons. And I still, to this day, have to think that through because it's confusing. Oil rig, it works. So that was talking about a complete transfer of electrons making ions. We can also have kind of a partial transfer where maybe things were shared evenly and now they're just shared unequally. It's not that you've made ions, but there's an imbalance in that electron density. So here we have a hydrogen molecule. These two hydrogen atoms are identical. They're going to share their electrons in the bond very equally. And here we have chlorine, the molecule Cl2, it's sharing its electrons very nicely because each of the chlorine atoms are equally strong, equally attractive to the electrons. When these react to form hydrogen chloride, so here hydrogen chloride, this if it was dissolved in water we'd call it hydrochloric acid, but here it's the pure substance. When hydrogen and chlorine share electrons, they don't share equally. Chlorine hogs the electrons. And so now we have a partial transfer of electrons from the hydrogen to the chlorine. The chlorine end of this molecule is a little bit negative. The hydrogen end is a little bit positive. It's not an ionic compound, but you can see how when this dissolves in water, how it might ionize very easily, right, and come apart. So the chlorine has gained electron density. The hydrogen has lost electron density. Reduction is gain. The one that gained is being reduced. The chlorine gets reduced. The hydrogen gets oxidized. Okay? Any questions? Well, when we're looking at those reactions between nonmetals, it's a lot harder to identify which one is gaining electron density and which one's losing electron density. With the ions, it's easy, but it's a little harder when you've just got nonmetals. So we use something called oxidation states. They're also called oxidation numbers, just to help us keep track of where electron density is shifting around. It is very important to understand that oxidation states are not ion charges. They aren't. They're just a kind of a bookkeeping method. They're imaginary charges that we assign based on a set of rules. We made this up. Okay? Ion charges are real and measurable. These are imaginary charges, but they help us to figure out what's being oxidized and what's being reduced. What makes it confusing is that an oxidation state is often the same value as an ionic charge. And so you see that enough and then you start to think that they're charges, but they're not. So here are the rules for assigning oxidation states. And these go in order of priority. So you go through in order. Free elements have an oxidation state of 0. Oftentimes, the oxidation state is equal to the charge. So free elements, sodium, the element, oxidation state, 0. Chlorine, the element, 0. Those are free elements. If you have monatomic ions, their oxidation state is the same number as their charge. So in NaCl, we know that this is an ionic compound. It's sodium ion, Na+, and chloride ion, Cl-. So the oxidation state of sodium is +1, and the oxidation state of chlorine as chloride is -1. The sum of the oxidation states of all the atoms in a compound is 0. So the oxidation states of everything in a compound is going to add up to the overall charge on the compound, which is 0. So we see that in sodium chloride, we have sodium with a +1 oxidation state, chloride with a -1 oxidation state. Those two numbers add up to 0. Do you see how the oxidation states behave a lot like ionic charges? That's why they're easy to confuse. It also makes them easier to remember how you assign the rules, because so far it's just the same as charges. In a neutral molecule, here we're talking about molecular compounds. The oxidation states will add up to 0. If you have a polyatomic ion, the oxidation states will add up to the charge on the ion. So if we look at NO3 minus, the nitrogen has a +5 oxidation state. I haven't explained to you how you would know that yet. It's coming. The oxygen has a -2. There are 3 oxygens. All the oxygens have the same oxidation state. So there's 3 that have -2, so that's a total of -6 oxidation state. And there's 1 nitrogen with a +5, and all of that adds up to -1, which is the overall charge. Okay? In compounds, metals are going to have positive oxidation states, and their oxidation states are going to be the same as their charges, the same numbers. So the group 1, always +1. Group 2, always +2. If you have transition metals, they can have different charges, they can have different oxidation states. The oxidation state is the same number as the charge. Now this is where we need to understand a new thing, or learn a new thing. So the rest of that was all basically the same as charges. Nonmetals. So we have a list of rules here, and these also go in order. It's a list of rules within a list of rules. Isn't that lovely? So this is basically an order of priority. Fluorine gets what it wants first. So fluorine gets what it wants, then hydrogen, then oxygen, then we go to group 7A, nonmetals, group 6A, group 5A. So fluorine, well, if it was an ion, what charge would it have? -1. So I think of it this way, that fluorine wants to have an oxidation state of -1. So in an ionic compound, it will have that charge, and the charge is the same as the oxidation state. But in a compound, a molecular compound, fluorine doesn't have a charge, but we assign it an oxidation state equal to the charge it normally has. Hydrogen. The hydrogen ion we're familiar with is a +1. I think of hydrogen as wanting to have a +1 charge. So it gets second choice, and oxygen wants to be -2 just like its ion. What charges do the group 7A nonmetals form? -1. So they would like to be -1. Group 6A makes -2 ions. They want to be -2. Group 5A makes -3 ions. They want to be -3. So again, oxidation state looks like almost a twin of ionic charge, right? The numbers are usually the same. What we do here, let's say we had, we're going to have some examples, but I'm going to make up one now. Let's say we had PCl3. That's a molecular compound. Phosphorus trichloride. There aren't any ions in it, so we can't look at charges. So phosphorus and chlorine, how do we pick what the oxidation states are? We go down this list. Fluorine, hydrogen, oxygen, group 7. Oops. Now we have to go through the parade of pointers. Ah, shoot, I overshot it. There we go. Okay. Group 7. Oh, chlorine's in group 7. So then chlorine gets its choice before phosphorus. Phosphorus is in group 5A. So chlorine gets what it wants. What does chlorine want? -1. So the chlorine gets -1 for its oxidation state. And then phosphorus has to make up the difference. So we have 3 chlorines. They each have an oxidation state of -1. That's a total of -3. All the oxidation states have to add up to 0, just like the charges would in an ionic compound. So what's the oxidation state of phosphorus? +3. Okay? So if you understand that subtle difference, it's a lot like charges. Now, another trick, how do you remember the table? I'm not going to give that to you. So this is what I came up with. Because, you know, some of these things I struggle with too. Have you ever had pho? I believe it's Vietnamese noodles, a noodle soup sort of thing, really yummy, right? So pho, this can actually help us remember. So the order here is FHO. Okay, well this isn't quite F, but what if we just take a piece off the P? And it makes the F sound, right? I know I'm reaching a little bit, but it works for me. So I think pho, 765. Fluorine, hydrogen, oxygen, 765. We're just working backwards on the periodic table. That's how I remember it. We'll do some examples. You can have fractional oxidation states. Can you have fractional charges on an ion? Nope, not possible. You either have lost 1 electron or 2 electrons. You can't lose 1.5 electrons. Oxidation states are imaginary, so we can have half of an imaginary oxidation state. And then as convention, to help us be less confused, I think that's the purpose, we write the sign before the number for oxidation states, after the number for ionic charges. So that's why these oxidation states, -1, +1, -2, -1, instead of like we would do with charges, the charge on an oxygen ion is 2-, right? But the oxidation state is -2. I'm not going to trip you up over that. You know, I'm not going to trick you and try to get you to answer a question wrong on an exam. But you'll see that sometimes the negative sign is in front and sometimes behind, and that's the reason right there. It's not random. I'm doing it on purpose. Let's do some examples. So, assign an oxidation state to each atom in each element, ion, or compound. Okay, so the first one is chromium. What's the oxidation state? 0. This is an element. It's all by itself. No charge. How about chromium 3 ion? +3. The charge is 3+, the oxidation state is +3. This is carbon tetrachloride. So there are 4 chlorine atoms, and there's 1 carbon atom. And so as we go through that list, it was, you know, elements and monatomic ions and polyatomic ions and blah, blah, blah. Here we're down to that table. And so we say Pho 765. There's no fluorine, there's no hydrogen, there's no oxygen. Chlorine's in group 7. So what does chlorine get to be? Chlorine gets to be -1. Because it's in group 7A, that's the charge it would take if it was an ion. There are 4 of those, and so they're all going to have the same oxidation state, because how would you decide, well, this chlorine gets to be -1, but that one has to be -2. There's no reason for a distinction there. They're all the same. And so I blanked on what it was. Carbon. It's not copper. It's carbon. Then how do we figure out carbon? That's where we go to the rule where all the oxidation states in a neutral molecule have to add up to 0. So each chlorine has an oxidation state of -1. That's -4. So the carbon must be +4. How about SrBr2? Well, what kind of a compound is it? It's ionic. So this has 2 ions in it, right? It has strontium ion and it has bromide ion. Those are both monatomic ions. The oxidation state is the same as the charge. So that's a lot less thinking. So for the strontium, it's +2 oxidation state. For the bromine, it's a -1 oxidation state. Any questions? SO3. What kind of a compound is that? Molecular. So skip past the first rules and say Fa765. Fluorine, nope. Hydrogen, nope. Oxygen. Oxygen gets to choose before sulfur. What is oxygen like? -2. Sulfur would also like to be -2, but oxygen gets to pick first. So then sulfur has to make up the difference. What's the sulfur going to be? +6. Wow, that's pretty different from what it would like, huh? Any questions yet? Okay, and then that last one, nitrate ion. Okay, this is a polyatomic ion. It is a nitrogen and 3 oxygens covalently bonded together, and overall it has 1 extra electron. So we're still going to go through the list. Fa765, oxygen gets priority over nitrogen. Oxygen gets to be -2. You'll see that oxygen usually gets to be -2. Well, there's 3 of them, so that's 3 times -2 is -6. And I'm looking for something for nitrogen that will add to -6 and give me -1. What's the nitrogen? +5. Okay. Any questions? This topic is one that makes some students crazy. It just drives them bananas. Just keep asking questions. Once it clicks, you're like, oh, that's not so bad. How do we identify redox reactions? Well, this is where oxidation states come in handy, because when we look at a reaction like this, carbon plus sulfur forming carbon disulfide, we don't see ions where electrons were transferred. You get 2 nonmetals forming an ionic compound, you can see clearly, oh, the metal lost electrons, loss of electrons. Oxidation is loss of electrons. It was oxidized. So we're going to use oxidation states to tell us, is this a redox reaction? And if so, what's being oxidized, what's being reduced? So here, carbon is an element, oxidation state 0. Sulfur is an element, oxidation state 0. In this compound, Fa765, sulfur, group 6, is the first one we come to. The sulfur gets to be what it wants, which is -2. And so that the oxidation states add up to 0, there's 2 of these, that would be -4. There's 1 carbon, it must be +4. So now we can see that oxygen, there's no oxygen. I was looking at the 0. That carbon goes from 0 to +4. Well, if that was a charge going from 0 to +4, would that be oxidation or reduction? It would be losing electrons. It would be oxidation is loss of electrons. So this has gone up in oxidation number. That is oxidation. The sulfur goes from 0 to -2. If those were charges, that would be gaining electrons, oil rig. Reduction is gain. So that's reduction. This is one thing I like about oxidation states, is I look at this number, it went from 0 to -2. Is that increasing or decreasing? It's decreasing in number, right? Number value, going from 0. If I had 0 money and now I owe somebody $2, my financial status has decreased. It's been reduced. Going lower in oxidation state is reduction, because your oxidation number is being reduced. Does that make any sense? It makes sense to me. Okay, let's do a problem. Use oxidation states to identify the element that's oxidized and the element that is reduced in the following redox reaction. Now, we do have a metal here forming an ionic compound, and so we could look at the charge on the tin ion and identify whether it's oxidized or reduced. But then we've got H, N, and O over here, and it's going to be a mess. So how do we know which of the others is taking up the slack? So we're going to assign oxidation states. Well, what's the oxidation state for tin, SN? 0. I like to skip around and do the easy ones first. This is an ionic compound, right? Ionic compounds are easy because the oxidation state is the same as the charge. So what is the charge on that oxygen, oxide? It's -2. It's an actual ion. It's -2. So what's the charge on the tin ion? +4. Those are charges on monatomic ions. The charge and the oxidation state are the same number. What do you want to do next? Okay, we'll do nitric acid next. Nobody has a preference. Here we have 3 nonmetals. Fa765. Fluorine? Nope. Hydrogen? Yes. What does hydrogen get to be? +1. Next on the list is oxygen. Oxygen gets what it wants, -2. Nitrogen is last. We figure out the oxidation state of nitrogen by looking at the rest of them, and all of them have to add up to 0. It's going to be +5, yeah. So if we take these guys, there's 3 -2s, and we've got a +1. So that ends up being, what, -5, right? So between the hydrogen and the oxygens, we have -5, so that means the nitrogen must be +5. I'm just going to stick it up here so it doesn't get confusing. Any questions on how I came up with +5? I'm going to erase this because it's going to be in the way.
So you don't carry that 4?
No, the 4 just tells me there are 4 molecules or 4 moles of nitric acid. It has no bearing on what's happening inside the molecule. Okay, how about NO2? Who gets preference, nitrogen or oxygen? Oxygen. So it gets what it wants. It gets to be -2. And what does the nitrogen have to be this time? +4. And then we come to water. Who gets preference? Hydrogen. Hydrogen wants to be +1, so it gets to be +1. That would be 2 +1s, so oxygen gets to be -2, which happens to be what it would like to be anyway. So I think of water as a happy molecule. Everybody's got what they want. Those are our oxidation states. Any questions? To find out what is oxidized. What's oxidized? What's reduced? Reduction means the oxidation state is going lower, more negative. So let's see what's happening here. Tin is going from 0 to +4. That's going up, isn't it? That's oxidation. What's happening with the hydrogen? +1 to +1. Nothing. What's happening with oxygen? -2, -2, -2, -2, nothing. The nitrogen is changing, though. It's going from +5 to +4. Its oxidation state is going down. It's being reduced. That's the reduction. This is super clear. I didn't plan that out very well. I should put that equation in the middle so I can go on top and on bottom. I will never remember to do that. The tin reactant is being oxidized. The nitrogen in the nitric acid is being reduced. Any questions? So oxidation and reduction have to occur simultaneously, because if one is gaining electrons, somebody else must have provided those, even if it's just a partial thing. Okay, so we've got something being oxidized and something enabling that to be oxidized. We've got something being reduced and something else enabling it to be reduced. So we're going to introduce agents. So let's talk about the movie business for a minute. Who stars in a movie? The actors. The movie stars, right? Who gets the movie stars their jobs? The movie agents. Do the movie agents star in the movies? Nope. Okay, so we have things that are being reduced, and then we have reducing agents. Does the reducing agent get reduced? Nope. It gets something else reduced. The reducing agent is what causes the other reactant to get reduced. And likewise, the oxidizing agent causes the other thing to be oxidized. Well, if I'm causing something else to be oxidized, then I myself am being reduced. So the reducing agent gets oxidized, the oxidizing agent gets reduced. You hate that, right? It's terrible. It's so confusing. That's why I'm talking about movie agents. So the reducing agent doesn't get reduced. Just like a movie agent doesn't star in the movie. It causes something else to do it. Try to remember that.
So,
yes?
in that last problem, then the oxidizing agent would be the same.
Yeah, so let's look at this. So the tin is being oxidized. It is causing the nitrogen to be reduced. Tin is the oxidizing agent. Nitrogen is the reducing agent. No, I said that backwards. Oh, that's just awesome. Tin is being oxidized. It is the reducing agent because it's causing this to be reduced. Nitrogen is being reduced. It is causing the tin to be oxidized. It's the oxidizing agent. The only way I can do those, and I've been teaching this for years, I have to think it through. I say, okay, well, this one's being reduced, so opposite, it's the oxidizing agent. Agent means it's the opposite. And it's going to be confusing. I'm sorry. We just have to go with what everybody else decided sometimes. Okay, I think this is where we were. Determine whether or not each reaction is a redox reaction. And then for the redox ones, identify the agents, oxidizing and reducing. So we may or may not have to use oxidation states. They didn't tell us we had to. Okay. So let's look at this. Here we have a metal and a nonmetal. They are reacting to form an ionic compound. Just by pattern, you can say that is a redox reaction. And by looking at actual charges, you can see that we're going from lithium with no charge. What's the charge on lithium in the compound? 1+. So the lithium has lost an electron. And chlorine has gone from no charge to a -1 charge, has gained an electron. So we can identify the agents in here based on the charges. The charges are the same numbers as the oxidation states. So if it makes you feel better to think about them as charges, that's fine. You're going to come up with the same answer. So yes, this is redox. So let's do oxidizing agent first, since it's listed first. The oxidizing agent is the one that gets reduced, right? Reduction is gain of electrons. Who's gaining electrons, lithium or chlorine? chlorine. So the oxidizing agent is the chlorine. And the reducing agent must be the tin. There's no tin. What am I saying? Lithium. I got here at 8:30 this morning because I had to cover somebody else's class. I'm going to be a basket case by the end of lab. Oh, there's tin down here. Maybe that's what I was looking at. Any questions about number 1? Good. Okay, this one. Just look at it. What do you think? Is that redox? Are things gaining and losing electrons? Yeah. Here I've got aluminum, and here I have aluminum 3+. Here I've got tin 2+, and here I have tin by itself. This is a net ionic equation, and it's like naked, right? We can just see what's happening. Up here, we didn't see charges. Here we're seeing charges. That's definitely a redox reaction. Okay, so oxidizing agent, that's the one that is being reduced, right? So who's getting reduced? Reduction is gain. Oil rig. Reduction is gain of electrons. Who's gaining electrons? Aluminum or tin? Tin. Tin is gaining electrons. It's going from a +2 charge to 0. Reduction is gain, yes. So SN2+, it has to be the reactant. If we think of that in terms of oxidation states, this is an oxidation state of +2, and it's going to an oxidation state of 0. That is being reduced. It's going down. What's my reducing agent? The one that's being oxidized is the aluminum. It is losing electrons. Oxidation is loss of electrons. Okay, any questions? People are starting, your eyes are starting to glaze over. Blink a few times. Try to focus. 3, is this a redox reaction? There's ions involved. Are any of the ions changing their charges? No. This is one of those precipitation reactions. Lead and nitrate went to the party. Lithium and chloride went to the party. They swapped partners, and lead and chloride are necking on the back. They went off by themselves. This is Pb2+, and over here, still Pb2+. No gain or loss of electrons. Nitrate had a -1 charge. Over here, nitrate still has a -1 charge. Lithium was +1, lithium still +1. Chlorine's -1, chlorine still -1. Nothing happening in terms of electrons being transferring. We're just swapping ion partners, not a redox reaction. How about that last one? Yeah. How do we figure out what's being oxidized, what's being reduced? Oxidation states. Well, the first two, the reactants are easy. They're both elements. They're going to be 0. Carbon dioxide, Fe765. FHO. So oxygen gets to be -2. What does the carbon have to be? +4. So we've got carbon going from 0 to 4, and oxygen going from 0 to -2. So this is a redox reaction. Our oxidizing agent is the thing that's being reduced. Whose oxidation state is going down? Oxygen. It's no coincidence that oxygen is an oxidizing agent. That word oxidation came from things reacting with oxygen. Carbon then must be the reducing agent. Because carbon is being oxidized. We can see it clearly in this one. Here, carbon had no oxygen. Now carbon is attached to oxygen. It's been oxidized or oxygenated. It's got oxygen now. And that's where the original term came from, was things reacting and having more oxygen. That's oxidation. But now we know what's actually going on, and so we do need to think in terms of oxidation states and charges. Yes?
So, number one,
Mm-hmm.
how were the charges for lithium and chlorine not or the oxidation state for it not set?
Okay, so in the reactants we have elements, right? So those are 0. In this compound, this is an ionic compound. It has 2 ions, lithium ion and chloride ion. They have actual charges. These are monatomic ions. For monatomic ions, the oxidation state is the same as the charge. So lithium has a +1 oxidation state. Chlorine has a -1 oxidation state. So when we go from 0 to -1, the chlorine is being reduced. That means it's the oxidizing agent. And the lithium is increasing in number. It's going from 0 to +1. Or we can think of that as oxidation is loss of electrons, so it must be losing an electron. So it is being oxidized. It's the reducing agent. Got through that one. Really, I think the only way to be able to do stuff like this is to be able to talk through it in your head. You don't necessarily have to write anything down, but be able to talk through it. Practice doing it out loud, because when you come to take a test on this, I can't have you talking out loud. But if I look and I see your lips moving, I won't laugh. I'm like, you must be doing a redox problem. Any other questions? You can do this. It's not that bad. So, combustion reactions. I'm dying. Okay. Combustion reactions are characterized by a substance reacting with oxygen to form oxygen-containing compounds. And so, as we were just talking about what does oxidation mean, something reacting with oxygen, that's going to be a redox reaction. Combustion reactions also emit heat. And so all of our combustion reactions, and when you think of the word combustion, what do you think of? Fire, explosions, stuff burning, right? Why do we burn stuff other than it's fun? Because it gives off heat, right? Why do we burn natural gas in a stove? That's not so fun, but it makes things hot so you can cook your food, and eating is fun. So methane is the primary component of natural gas. It reacts with oxygen in a combustion reaction, and the products are going to be carbon dioxide and water. And if we look at the oxidation states, here they did it for us because we've had enough practice for right now. The carbon went from -4 to +4. It went up. The hydrogen stayed at +1. The oxygen went from 0 to -2. So the oxygen is being reduced, right? It's going from 0 to -2. It is the oxidizing agent. The carbon is being oxidized. It's the reducing agent. Write a balanced equation for the complete combustion of liquid C2H5OH. That's ethanol. Well, so here's our, let's start out with the formula correct. That's always nice. C2H5OH. What's the state of that? The liquid. Now what do I do? What's required for combustion? Oxygen. The other reactant is O2. What do you think the state of O2 is? It's a gas. So that's what we're starting with. doesn't say anything about temperature. We're going to assume room temperature. Oxygen is a gas at room temperature. You have to get this reaction started with a spark or a flame, and then it burns. When your thing that's burning, there's probably a better name for that, thing that's burning, if it contains only carbon, hydrogen, and oxygen, or just carbon and hydrogen, the products are always the same. CO2 and water. So I shouldn't need to tell you what the products are. You should remember, oh, that's a hydrocarbon burning, I'm going to get CO2, and I'm going to get water. It's combusting. What's our best guess as to the temperature of the products? Hot or cold, or room temperature? Hot. So let's assign the states based on what we can deduce about the temperature. What's the state of carbon dioxide when it's hot? It's a gas. It's a gas even when it's cool. How about water? Gas. This is why you don't see water pouring out of flames, but there is water being produced. And then we have to balance it. These combustion reactions are the ones that most often end up needing fractions or the odd-even problem. Let's see what this one is. Okay, I like to start with carbon. There's 2 carbons, and over here I have 1 carbon, so I'll fix that by putting a 2 in front of the CO2. I definitely want to leave the oxygens for last, because I can always fix them with this guy. So I'm going to do hydrogen next. So here I've got 5 plus 1. Don't overlook that one. So I've got 6 hydrogens, and over here I've got 2. So if I put a 3 in front of that, I'm good. There's oxygens everywhere. Be careful when you count them up. How many do I have on the right side? 7. I've got 6 from the I've got 4 from the CO2. And I've got 3 from the 3 water molecules. So I have a total of 7 oxygens. How many oxygens on the other side? Well, currently I have 3. I have 1 over there, and I have 2 there. Is there a number I can multiply 2 by so that when I add 1, I get 7? 3. So if I put 3 in front of O2, that'll give me 6 oxygens from the O2, plus the 1 from the ethanol will give me a total of 7. And there's my balanced chemical equation. Any questions?